Next we have Alexandra Kolla. She's going to tell us about spectra of matrix signings.
Thanks for inviting me and being here. This is joint work with Charlie, who's my student over there, another student, and all these people that are not really existing anymore. Okay, and maybe this will be a short talk because I have to move my car, so I don't know. We'll see how this goes. Okay, so I'm serious. Like I got a $70 ticket last time in some situation like this. Okay, so hopefully everybody knows about how to represent graphs via adjacency matrices. This is pretty common in all aspects of mathematics and computer science. Whenever there is an edge with some weight, you create this matrix, and entry ij corresponding to nodes I and j has an entry with that weight inside there. This is an adjacency matrix, and since it's a linear operator, it has eigenvalues and eigenvectors like linear operators do. We call the spectrum the set of eigenvalues usually ordered in decreasing order, lambda 1 through lambda n. And spectrographs have received a lot of attention from both theory and practice of computer science. The most sort of important reason why this had happened, in my opinion, is their relationship with partitioning, clustering, cutting graphs. And in practice, this has a lot of applications in network reliability. If you want to build a road, you want to kind of like your network to be well connected so that when one bridge fails, the two parts don't just all of a sudden become disconnected and you can go from one place to another. Community detection in Facebook, et cetera, et cetera. And this is captured by what we call the relationship between spectrum and sparsest cut. Sparsest cut, for those of you who don't know, is just the minimum ratio over all partitions of the graph of the edges crossing the partition over the smallest size of the cut. This is the, and I don't know where the clicker that, oh, is that it?
I'll try it out.
Yep. That's it. Okay, so this is the sparsest cut, and the celebrated theorem by Chigger relates the spectrum of this adjacency matrix with the sparsest cut. Why do we want to do that? Sparsest cut is a quantity that unfortunately is NP hard to find. So even though all these applications that I mentioned would like to find the sparsest cut so that to make sure there are no sparse cuts, or so that they cluster communities in Facebook or whichever other application you want, you cannot do that efficiently since it's NP hard, unless p is equal to NP. And Chigger's inequality is kind of like the next best thing. It says that if I already look at this linear operator and its second eigenvalue, which I denote by lambda 2, and this is for d-regular graph, but it holds for any, there is a version for any degree. Then this d minus lambda 2 is a very good approximation of this NP hard quantity I wanted to find, the sparsest cut. So I'm going through all this very quickly because it's, most of you know this already and it's irrelevant to what I want to talk about. What I'm going to look at today is kind of like resembling this adjacency matrix representation of graphs that we had, only okay, you use graphs to matrices to represent, let's say, social networks or any graph like the Facebook graph here, and you put this edge between A and B if A and B are friends. This is what we already talked about. But what we didn't talk about is like, okay, let's say A, B are friends on Facebook, but they're Republican and Democrat, and they really dislike each other, and they post all these mean comments that you see sometimes between the. I mean, I have two Republican friends, I think, and we're completely different in what we post. But it could be the other way around, and you're like, okay, what if A and B dislike each other? How do you capture this? This got suggested already in the 50s, I think, by Harari first, to capture this dislikeness, even if A and B are friends and there's supposed to be an edge between entries A and B of this matrix, you put a -1 instead of a 1. So if A and B like each other, there is an entry with with 1 in this matrix. If A and B dislike each other, there is a -1, and we call this the signed adjacency matrix of a particular graph denoted by A of S, and it would be a signed adjacency matrix for any signing. So any number of entries could have -1.
Why should this not be a directed graph? What if A likes B, but B hates A?
It could be, but what we talk about today is about symmetric matrices in particular. So yeah, this is very possible, but it's much harder to analyze mathematically, so I'm not going to talk about this today. Okay, so this is the signed adjacency matrix. This is where it came from, already, as I said, in the 50s, I think. But why would we care, and why am I talking about this even today? So recently, there was, I mean, not so recently anymore, I guess. There was this program by mostly Dan Spilman, Nikhil Srivastava, and Adam Marcus that they were trying to prove the Carrington-Singer conjecture, which they eventually did. But in the process of this, they showed something about expander graphs. So just quickly, for those of you who don't know what expander graphs are, and Ramanujan expanders in particular, we looked at this lambda2 that approximates sparsest cut. So graphs that don't have sparse cuts, graphs that are very well connected anywhere you cut them, are expander graphs. And it's kind of like clear why you would want those. For example, if you think about the road application I gave you, the network needs to be well connected, so there are no ways to separate the network, and all of a sudden it has some problems. So expander graphs are graphs with no sparse cuts. In other words, they are graphs where lambda2, the second eigenvalue of the adjacency matrix, is as far away from lambda1 as possible. Lambda1 for D regular graphs is always D. So lambda2 has to be as far away from D as possible. And the furthest away it is, the better the expander is that we can see with Chigger's inequality. Okay, so it has been a really interesting question in mathematics. Can we, do those graphs even exist? What's the best lambda2 one can get? And I'm not going to get into much of this. But it turns out for D regular graphs, the best lambda2 you can get is 2 square root of D minus 1. So let me write this down here, since this is a theorem by Alon Bopanna. Lambda2 has to be at least that much. And it turns out that there are graphs that achieve this. They're called Ramanujan graphs. And for the purposes of this talk, we would call them the best possible expanders, because they achieve the best possible bound on lambda2. So this program by Marcus Spilman and Srivastava showed that there exist these graphs for any possible degree. Before their work, the only existential result that was there was by Lubotsky, Phillips, and Sarnak that showed that if the degree is prime or some prime power, then you can construct Ramanujan graphs for those specific degrees. But then this more general thing by Marcus Spilman and Srivastava came, where they said, yes, they exist Ramanujan graphs for all degrees. And the way to do that, they did it with what we call a two-lift. So a lift of a graph, we'll see in a second, is just a bigger graph. So you start from a good, really small graph, let's say the complete graph on 5 nodes. And then you lift it, which I'll explain what lifting operation is, and you hope to preserve the eigenvalues. So complete graph is the best possible expander. If you lift it and nothing changes, the eigenvalues remain bounded, then you have a bigger graph that's best possible expander, and then you lift it again, et cetera, et cetera. Eventually, you construct arbitrary families of Ramanujan graphs by lifting. So what they showed is that there exists always a two-lift of a graph that achieves this Ramanujan bound. And then we also used lifts for a quasi-polynomial time algorithm to construct almost Ramanujan graphs. So there's a lot of, and there are other results that I'm not mentioning here, literature on, yes?
Do you need the MSS, do they need the graph to be Ramanujan to begin with? Or?
Well, if you want to eventually have Ramanujan graph, we will see in a second. But in general, I mean, the result they showed is independent of that. But if you put it together, you need the graph that you start with to be Ramanujan for the end graph to be Ramanujan, because the old eigenvalues always live. So, okay, so, and see, here's what two lifts are, and you will see that this is exactly signings and signed adjacency matrices. So a two-lift is a graph that has exactly twice as many nodes as the original graph. And what I do is if the original graph had an edge, and so a two-lift is exactly assigning. I start with a graph that has an edge between I and j, and I have two choices. So I put, instead of one vertex, two vertices for every vertex, and I have two choices. One is the +1 signing, which would correspond to a matching between these 2 and 2 vertices. That's what we call the identity matching, or the cross. So if I lift an edge, this operation is called lifting an edge, according to what you see on your left. This corresponds to a +1 in the signed adjacency matrix. And if I lift it like this corresponds to a -1 in the signed adjacency.
Vertex is split into 2 vertices?
It's what's the word?
Split.
Okay, split, fine. So I replaced by 2 vertices, yeah. Split in 2 vertices.
The new graph still has weights, +1, -1, or every...
Let's say it's unweighted, but yeah, the weights remain the same. Every edge would have wij in here. But let's say now it's unweighted. So the new graph just has, instead of one edge, it has 2 edges. So if this was vertex I, this was vertex j, I split vertex I into 2 vertices. I split vertex j into 2 vertices. There was one edge between I and j. Now I have 2 edges between this tuple of vertices. And the 2 edges could look like this or could look like this. These are the 2 options that you have. And it turns out that this signed adjacency matrix that we saw, so if you just take those choices, those signs, and you write down the signed adjacency matrix like we saw before with the Facebook example, is all you need to guarantee or figure out, I guess, whether or not your lift is a Ramanujan graph or not. The reason is because the adjacency matrix of the bigger graph that has 2 n vertices can be written like this, and is not very hard to see by this expression, A, that this is correct, which I'm not going to show, and B, that the set of eigenvalues of this lift graph is the union of the eigenvalues of the original adjacency and the sign adjacency. So sign matrices and signings of adjacency matrices became popular, I think, lately more so because of this connection, that if you were able to bound the eigenvalues of AS to make them as small as possible, then you will be able to construct Ramanujan graphs. So here's a type of question that would be enough in order to present a polynomial time algorithm to construct such graphs, because all these results are existential and we still don't know how to find a lift efficiently that achieves the bound that's guaranteed by the theorem. And I have to say that Michael Cohen had a result that makes one of their proofs constructive, but it doesn't have to do anything with lift, so I'm not going to go into that. However, let's look at the following problem. We call it bounded eigenvalue signing. I'm giving a real symmetric matrix and some number lambda, some real number. And the question is there a symmetric signing of this matrix such that the largest eigenvalue of the signed version of this matrix is at most lambda? And if I could solve this problem efficiently, then I could, and constructively, let's say, then I could find the Ramanujan graph, because I set lambda to be 2 root d minus 1, and I have my answer there. So one thing that we show in this work is that this problem is NP-hard, which kind of kills an approach along those lines for efficient algorithms for Ramanujan graphs. Any questions? Okay. So, however, this is not what I want to focus on, even though that was the original motivation for this problem. We started trying to find an algorithm to build Ramanujan graphs, and we were stuck majorly an algorithm along those lines. We ended up proving this is NP-hard. And then we started asking other questions about graph signings. So for example, given a real symmetric matrix M, is there an off-diagonal signing, symmetric again, such that the M of this signed adjacency matrix is non-singular? In other words, the determinant of it is non-zero, or all the eigenvalues. There's no eigenvalue that's equal to 0. And we ended up also resolving this, and I'll give you a motivation for why this is interesting. So let's look at a well-known randomized algorithm for bipartite matching. So this is due to Lovaas in the 60s, I think. It's based on polynomial identity testing as follows. So we construct the matrix that's called the TAT matrix of the graph. This is a matrix where every edge is replaced by a variable, xij. The specific matrix was skew-symmetric, so xij is minus xji. And a result by TAT says that the determinant of this matrix is not identically 0, so it's not the 0 polynomial, if and only if there exists a perfect matching in G. So the graph is bipartite, and we're trying to design a randomized algorithm to check whether or not there exists a perfect matching in this bipartite graph. Okay, so here is a randomized algorithm that's implied by this theorem. So we can choose xij randomly from the real numbers, evaluate the determinant polynomial of this stat matrix, and with probability 1, I will not hit roots of this polynomial if I choose xij from the real numbers. Thus, we get the correct answer with probability 1. However, we need infinite randomness to do it, properly, to choose from the real numbers. What people have done, what Lovaas did, was instead we choose some finite field, let's call it S, and we choose elements R1 through Rn from this finite field, evaluate the polynomial on these values from this finite field, and if I get 0, I return answer is the 0 polynomial. If I don't get 0, I return answer is not the 0 polynomial. And by Schwartz-Zippel-Lima, I know that the probability that a non-zero, non-identically 0 polynomial evaluates to 0 with this random choice is less than or equal to d over s, where d is the degree of the polynomial and s is the size of the field. So this would give us, for the determinant, we have a polynomial in m variables, 1 per edge. Degree is n, so it's enough to choose a field of size 2n to get probability of error less than a half. So this theorem by TAT could be made into a randomized algorithm by using that much randomness, log n times n, m, to choose one of the xij's from the field S of size 2n. So why these signings come into play is here's a natural question. Forget about choosing a field of from a field of size 2n. Can we just choose from F2? What if I restrict my xij choices to just be minus 1, 1? Is it still true that I can choose random minus 1, 1 for every variable, evaluate the determinant of this matrix, and get the correct answer with high probability? So now we consider the symmetric version of this matrix, not the skew-symmetric, but this is just a detail. So what we can show is that in some sense this is indeed true. So if there is a perfect matching in this bipartite graph, then there's always going to be a signing that makes the determinant non-zero. So this polynomial won't be the 0 polynomial. However, the probability of success of this can be exponentially low.
It's related to Nunstall sets.
So I'll get to that. Yeah, you read ahead. No, I'm kidding. Okay, so, but this is sort of the this is the first step to a more general result that says that not necessarily bipartite, but for an arbitrary graph G, for any graph G, the determinant of every signed matrix of this graph is 0, if and only if the support graph of, so for any arbitrary graph G, every signing of the adjacency matrix of Z has determinant equal to 0, if and only if the graph does not have a perfect 2 matching. So what is a perfect 2 matching? Real quickly, instead of just having matching edges, you can have cycles. So every node still has degree 2, and it's either because it has 2 edges belonging to a cycle or because it has like a back and forth loop. So perfect 2 matching is a generalization of matching where you're allowed to cover all the vertices by either using cycles or matching edges. Okay, so the theorem says that the only way for all the possible signings of the adjacency matrix to be singular is if there is no perfect two matching in the graph. So now here's a theorem, which hopefully, probably all of you know. It's the Alon's version of Nalstelanza. It's a combinatorial Nalstelanza that basically says if I have a multivariate polynomial and I have a term in this polynomial, the degree of each variable on this term is ti, and this is the non-identically zero polynomial, then I give you any set, S1 through S, any collection of sets S1 through Sn, but with the promise that Si size is bigger than Ti, where Ti was the degree of variable Xi, then I know, I am guaranteed that there is a tuple from this collection of sets such that the polynomial evaluates to non-zero. Okay, so basically this is an extension of if I had one variable and I give you, a polynomial of degree d and I give you d plus 1 points, then I could find a non-zero among those d plus 1 points, and this is the multivariate version of this thing. And this has been a powerful algebraic tool to show existence of certain combinatorial structures. It's similar along the lines of Lova's local lemma and Spencer's discrepancy theorem. For example, by applying this for the correct polynomial, you can prove that every simple 4-regular graph contains a 3-regular subgraph. And you can do that for other degrees and stuff too. I just have the simplest version here. However, in contrast to Lova's local lemma and Spencer, there is no known constructive proof of CN, combinatorial Nalstelanza. I'll call it CN because it's hard to say the whole thing. Okay, so in fact, Alon and West and other people have wondered about whether one can make combinatorial Nalstelanza constructive, because the other two things that we know how to prove existence of structures have been made constructive. And there was recently a result that shows that this problem is PPA complete under some circuit input models for polynomials, but I won't get into that much. What I do want to get into is that the proof of this theorem, first of all, follows from combinatorial Nalstelanza, even though there are many more proofs of this theorem. And the second thing that I hope to get to talk to, if I have a little bit of time, is that not only we can prove this theorem by CN, but we can also make it constructive. So in particular, if the polynomial is a determinant polynomial, then I can find a non-zero of this polynomial in polynomial time among the field of two elements. So do I have 5 minutes-ish? Okay, let me try to finish and not get a ticket at the same time. So let's try to see how we prove this. Define this polynomial, which is nothing but a restatement of the determinant polynomial. So determinant can be written as the sum over all permutations of the sign of the permutation and the terms that correspond to the permutation. And it's not hard to see that the only terms that survive are terms that belong to perfect two matchings. Otherwise, there would be some zero entry. If the graph is not, if the term is not covering a perfect two matching cycles or matching edges. And I can write this polynomial for some fixed coefficients that are what you get from the determinant. And consider now this polynomial. So here's the first claim is that the polynomial is identically zero if and only if the set of perfect two matchings is empty. And that's not very hard to see one direction. The other direction, let's consider the set of perfect two matchings is not empty, and pick a F in the set of perfect two matchings. Then there is a term, a monomial, that has non-zero coefficient that corresponds to this perfect two matching. And moreover, if there are other terms, other monomials that have the same variables in them, they would have the same sign. This is also not very hard to see because they have the same cycle edges and the sign of a permutation depends on the cycle edges. So consider this proved, even though I just went to it very fast. So if f is identically 0, if and only if the set of perfect two matchings is empty. And now let's prove this other theorem by Nalls-Stalanza. Okay, so if there is a perfect two matching, there is this term here, and there are variables with exponent either 0 or 1, so the degree of each variable is either 0 or 1. We know there is a maximum degree non-zero coefficient term. Immediately apply Nalls-Stalanza for SIs to be the set minus 1, 1. Note that every variable has degree 0 or 1, and the size of the set is 2, so it's bigger than 0 or 1, so we're in the right setting, and that's the proof. So again, unfortunately, we would like a constructive way to prove Cn, but we don't have any. So let's start restricting ourselves to special cases, like what if my polynomial is a determinant polynomial? Can I find a non-zero in polynomial time? It turns out I can. And I'm just going to speak like 30 seconds of how to do this. It's a recursive algorithm that uses a generalized version of two matching, which is a cycle cover. Cycle cover is between two possibly different sets of vertices, x and y, and it looks like this. So in the common thing, it's cycles, loops, or edges. And in the between the nodes in x but not in y and y but not in x, there are paths. It could be edges or any length paths. So this is a cycle cover, and there is a generalization of this other theorem that the determinant, there's a signing with non-zero determinant of this submatrix, M of S restricted to x and y rows and columns, if and only if there is an xy cycle cover. And there is a way to make this constructive. And by this constructive proof of this theorem, you get immediately a recursive algorithm that reduces the size of my graph that I'm looking for by one edge or by two vertices every time. And it runs all the time. OK, I think I'm right on time. Thank you.
Any questions for Alexandra?
Can you say a little bit more about the PPA completeness result? Do you know?
Actually, no. I mean, it's way beyond. It's a circuit complexity model that I have nothing to do with.
Does it mean that you cannot do it constructively in any sense?
Oh, I was going to solve the open problems. Thank you for reminding me. OK, so here's a bunch of open problems. One of the important open problems is, OK, we know that an input model that's PPA complete. Is there like any generalized input model that's also useful in some sense that admits, we can make it constructive? So this is, I think, the most important open question. In which cases can you make Cn constructive? I mean, clearly, if you're given the monomials explicitly, then fine. But what representation of polynomials that you're not giving the monomials explicitly are interesting? Yes.
Do you know if the special case for determinant that you consider, does it fall under PPA, the algorithm you have? Or,
I mean, it's polynomial time,
sorry?
the algorithm we have.
Right.
So you can find it already. Yeah. Does that answer your question?
PPA is a class, right? So this is a
I'm
special
sorry?
case of a problem. The
Sorry?
single problem is
Yeah, so is this special class, I mean, it's not beating that non-constructiveness result by coming up with a different technique. It's still within that class, but it's beating because it's a special case?
I mean, the input model is different. I can't compare the input models because I'm not very well versed in circuit input models for polynomials. So, but I can compare like how much, if the one is a special case of the other, or if there is determinant that cannot be given like this. I'm not sure. But nonetheless, identifying which input models can make Cn constructive, I think it's important. And then even if we cannot do that, for example, can we find 3 regular graphs of degree 4 3 regular subgraphs of degree 4 graphs. So the applications of CN, can we make those constructive by looking at those polynomials that give you, I mean, these are important open problems in graph theory. And if we have a general recursive algorithm to make anything constructive for CN, we might be able to solve these important problems in graph theory, even if we don't answer the first question. And then, there are things about expanders that need to be answered. But again, this is a different topic.
There are no questions. Let's thank Alexander.